Well, thanks everybody for being here. Just a brief introduction. My name is Zubair Talib. I lead a software and AI services company by the name of Solara. And thanks for having me here, Scale. Appreciate the opportunity to share a little bit about open source, voice understanding, and edge. So we're at an open source conference. So curious, how many people have actually worked hands-on with open source AI? Speech recognition, language models, vision models, anything? All right, awesome. How about voice AI? Any voice applications, voice assistants? Some, okay, great. And how about edge, embedded systems, any things of those natures? Raspberry Pis, Jetsons? Okay, awesome, great. Well, look, this talk, I wanted as many buzzwords as I can, so I got at least a few of them here. I wanted to talk through about open source AI and its application in voice on the edge. So we'll go through a little bit about the different parts of what's taking place in the space, and then we'll talk about a specific project. So, I mean, what's taking place in open source is really remarkable as it pertains to AI. I mean, I think everyone has seen big tech, particularly Meta, that's making huge investments in models like Llama. Chinese companies like Alibaba producing models like Qwen, Mistral out of France, and I'm sure everyone has caught the news about DeepSeek the last couple months, putting out incredible models of this type. So lots of activity from big tech and startups to compete with the closed labs. So I think this is one of the big things that's taking place. The other thing, clearly there's an ecosystem that's evolving around this, and I think Hugging Face is clearly at the lead of producing open source support for models. Tools like Ollama and LM Studio that make it easy for developers to work with. And then there's a lot taking place in the research community to be able to make these models work better in smaller capacity, distillation, quantization, low-rank adaptation, or LoRa, a mixture of experts, so a lot of different things that are taking place. So this confluence of, of capital going into startups and big tech tooling and so forth has led to a lot of progress in this area. For this particular case, from an edge computing perspective, we'll be talking about working with the NVIDIA Jetson, the Orin Nano, which is essentially it's a single GPU with multiple cores. It has about 16 gigs of memory, and in this case, used instead of a developer kit, used the Seed Studio recomputer, essentially a built, ready to go, fully assembled, ready to run AI models with. It already has 120 gigs of storage and peripheral connections and so forth, so easy to work with. Ready to go for this purpose. And then voice AI. So voice AI, there are a number of different aspects of voice AI. Voice understanding is the application we'll be talking about here. Basically the concept of summarizing and extracting insights. Everybody's used some sort of AI note taker in Zoom or Google Meets like Fireflies. Gong.io is a similar application for sales insights. Observe AI is one that works in call centers. The other big application, of course, is voice assistants and voice agents. So, of course, our Siri, Alexa are types. I did work on a drive-through assistant for fast food restaurants. Again, a voice agent and assistant that interactively does an activity. And really the last bucket is around voice transformation. So, like the Google Real-Time Translate or accent removal, companies like Sonus.ai and others that are doing real-time translation and or real-time, essentially, transformation, so listening and transforming. So why with voice AI at the edge? So there are an increasing number of applications, and because of the improvements in technology, that make interesting use cases for voice AI at the edge. Offline is the big one, of course, so you don't need the cloud, so working without internet in remote settings, or if there's low or not high quality internet. The other case that's come up is security, so where people don't want that information going up to the cloud, secure, not leaving the location, compliance, and otherwise. Cost efficiency, if you've got running something all day long, not having to use bandwidth or cloud compute, can run these in that kind of setting. Latency from the perspective of removing the round-trip delays to the cloud. And last is reliability. Again, if there's intermittent cloud failures or network outages or any of this sort, you have this, this device that can back up right there at the edge. So for the purposes of this talk, we'll go through a specific use case, and I'll walk you through the project and basically some explanation, understanding of this. So the scenario that we'll be working through is essentially a retail pharmacy. The problem statement essentially is to capture the pharmacist and the customer's interactions and essentially convert that into some sort of understanding and summarization. Basically transcribing the dialogue, summarizing the key points, and generating key insights from it. The requirements for the project essentially are that it should be locally processed due to spotty or limited internet connection, privacy and compliance, and secure data handling and storage. So all the reasons that we want to work at the edge. And really what we're looking for here is accuracy and latency in terms of how to define success for this project. So this is essentially the use case. I just realized I don't know if my audio is hooked up here. I'm going to try to put this here like this. So you can hear. Whoops.
Hello. I was wondering if you're doing COVID-19 boosters at this location?
Yeah, we are. Do you have an appointment or are you looking to walk in?
I was hoping to walk in. Is that possible today?
Yeah, we take walk-ins, but there might be a short wait. Let me check the current queue for you.
Sure, I can wait. Also, do you know which boosters you're administering?
We are currently offering the updated mRNA boosters. I'll confirm the exact brand when you are ready to fill out the consent form.
Okay, great. Hope you're able to hear that. Basically just a simple conversation between two people and trying to capture that, and this is the kind of thing that we're looking at. The type of insights that we'd be looking to generate is something like this, and sorry, it might be a little bit small to see, but basically like aggregating clinical consultation, service inquiries, prescription management, and then what happened in those kind of conversations. So what was the outcome, information provided, referral needed, and so forth. So some sort of structured insights by analyzing conversations in this way. So what we'll cover, we'll go through the approach and architecture for sort of building with this. We'll go through an AI model evaluation, like how did we evaluate the models that were used. I'll do a quick demo on some of the results, and then we'll talk about some of the learnings and recommendations. And we'll stop for questions at the end. So the approach we'll go through is, essentially the first is to sort of define a high-level architecture. We'll need to acquire some data to do some testing around. Essentially, we'll have to define the task around how do we summarize. We'll generate ground truth, we'll engineer some prompts, and then we'll build an evaluation framework to see how well it works. And then we'll do the design, build, and test and all that. So I'll go through it kind of quickly. So the basic approach is very simple, right? Customer, pharmacist are talking, there's a microphone. That microphone is connected essentially to a simple speech recognition, and then we'll use an LLM with a prompt, very basic, to summarize that conversation. So the speech recognition produces the transcript gets summarized, and it's out. So high level, it's quite simple in that regard. We needed to have audio data to actually test in advance of running it with a mic. So we couldn't use real customer data for something like this sensitive, so we simulated some data. As you heard, it was recorded. We generated a variety of simulated conversations, ChatGPT for help here, and we tried to do a different bunch of type and make it back and forth, different lengths and different things. Initially, we tested with text-to-speech, like in 11 labs or something, generating the audio, but we found that it unrealistically improved the quality of the speech recognition and the LLM. It was very standard. When you actually have real people speaking, you get a lot more interesting dynamics. So we recorded real human conversations for more realistic testing. So that was the conversation you heard, for example. So once that transcript is produced, we need to produce a summary, and we need to know how well that summary is working. So the most obvious is just say, summarize this conversation, right, in ChatGPT or some sort of LLM like that. The problem, of course, is that it's hard to evaluate which summaries are well and how to extract meaningful insights. So the next attempt was make a single categorization, say categorize this conversation in one category. This didn't provide enough fidelity, so then we went to multiple topics, and then from there, structured attributes. So this is essentially where we ended up, something like, okay, break the conversation down into topics, and for those topics provide a target, a context, and a resolution. So something like this. It was a service inquiry about the COVID-19 booster, the context was service scheduling, the resolution was information provided, and maybe there's some other facts. And really, the type and the resolution maybe are the main pieces, and you've got all this other at next level of detail. Now, JSON would be a natural way to produce this. You have conversation and JSON out, but the smaller models struggle to reason over multiple tasks. So in the end, we went with a very simple textual based, and we were looking mainly to capture the language understanding, not to test the multiple tasks in this way. So that's what ended up for the format. So with that format, essentially then we needed to generate a ground truth, some objective data to evaluate against. So the transcriptions needed to be updated, even though we produced the transcript and then someone, they read it, we needed to correct it for all the small variations and things like that that take place when people speak. We then also needed to provide this structured summary. So for each conversation, we had then a set of audio, a ground truth transcript, and a summarized conversation summary that looked something like this, right? Had one or multiple topics and so forth. So that then gave us essentially our ground truth data to be able to evaluate off of. Then what we started working on is the summarization and how we'd actually produce the summary. So with a conversation, we started let's just try again to produce that kind of output that we wanted. And essentially we started iterating to see how well that would work. We started expanding to see with multiple conversations and multiple cloud edge models to see how well we could get that prompt working just through that experimentation. And through the course of that, we ended up having to, beef out a prompt, add different rules, for example, like when should you split a topic, how should you decide to create a new topic. We ended up adding a controlled vocabulary for at least some of the attributes like the type and the resolution, all of this to sort of help in the inferencing. And the approach, it's a simplistic approach, but it's a helpful one to think about is you can actually use the LLMs itself to help you in this development process. So think of it, you start with the simplest prompt that you have, take a conversation and say, execute this prompt with this conversation. You'll get an output. Then we say, okay, take that output, and this is the expected output. What should the prompt be? So essentially what you do, you can try something like this. You say, this prompt should summarize this conversation and achieve this output. The current result is this output. Based on this comparison, make me a recommendation for a new prompt. And so you can essentially use the LLM to essentially prompt engineer your prompt, and it's LLMs all the way down. It's always fun. So it becomes a way at least to sort of work through this. Okay, so then with that summarization in place, the next thing is to sort of build an evaluation framework. So here you can see, you have a predicted summary, something like this, 2 topics, and you have the ground truth, and we essentially need to then evaluate how well did the summary that we predicted work against the ground truth and try to get some sort of scoring as a way to evaluate the models. So in this case, for example, you can see cough treatment and cough medicine, we can call those the same in this context, but ready for pickup and information provided are not the same. So we're not necessarily looking for exact match, maybe this we're looking for language understanding and just to see if we get the things that we care about. And so here, initially we attempted the very sort of traditional text similarity scores like cosine similarity or edit distance or trying to see the comparison between ground truth and summaries. But it's fragile because of the kind of things that we saw that have language understanding, not just semantic understanding that we needed to look through and alignment with multiple topics, and there's a variety of things to take care of. So we said, well, we've been using LLMs for everything, why don't we just use an LLM to evaluate? So here's the predicted, here's the output, use an LLM to score it. And this gives you some good information, but direction became difficult, and we found it to be unpredictable. Even with elaborate prompting and rules, we spent quite a bit of time. So in the end, we ended up using a custom approach that essentially a hybrid that would do some topic alignment, and then we use LLM to understand meaning of different topics, and then we would implement sort of the traditional precision, recall, F1 scoring, which these are the methods for classification numbers. And so this at least created a consistent benchmark across the models and one we were able to drive consistent behavior amongst. And again, for the purposes of this project, we didn't really focus too strongly on the formatting, different formatting and JSON and all that stuff. We were really mainly understanding the language understanding, and this gave us the ability to do that. So essentially we ended up with this, input and reference, topic alignment and comparison, and we'd get the scores, and you could basically get some understanding of what took place there. Okay. Okay, so then I gave you sort of the architecture that we'd have in the real world, but this is the development architecture, right? So we have audio files going through our system that runs on the Jetson. We'll get this summarized conversation, and then we have this evaluator. So we have these ground truths that we feed in, the audio transcript and the conversation summary. And then we have an evaluator, this evaluator apparatus that we described. And then we pop out the speech recognition and word error rate, and the summary evaluation by F1 precision and recall. And so this is the approach that we use for building something like this. And specifically from a code perspective, you can think of, in the Jetson, there's a piece that takes either a microphone or file audios and passes to a speech recognition set of services. For the purposes of this, we wanted to do benchmarking against cloud. So here we had, either cloud speech recognition systems like OpenAI or DeepGram, and then we had the edge processing, like in this case primarily Whisper. There was an event handler to pass transcripts, so you could also think of running the speech recognition in batch mode or in streaming mode, so you get events depending on the likes of the transcripts, and then processing these through an LLM. Again, we benchmarked cloud LLMs like through Grok and OpenAI, and then edge models primarily using Olama. So this is mainly the voice understanding pipeline on the left here. On the right, for the purposes of building this, we ended up building sort of a pipeline orchestrator, so that you could say if you have this speech recognition model and this LLM model and this prompt and this set, you could run a whole bunch of them, and then you could cache them so that if you're running the same transcription, you don't have to run it again, and you can evaluate it. And of course, there's a web demo that will show you could see these in offline. So all of that was essentially the orchestration evaluation piece of a project like this. Okay, so that was the basics of how we built the basic apparatus, and then we went to the model evaluation. So for speech recognition, we primarily focused on Whisper models. We spent a little bit of time with Conformer CTC, NVIDIA's model, but primarily spent time with Whisper. They're easy to use, and there's a variety to choose from, and so we spent time just looking at that, and mainly on the LLMs is where we spent the time. So here you can see that the Whisper Tiny and Whisper Base, these are the size of the models that Whisper has. They run at essentially, these are the word error rates, so the base model is better than the Whisper model. The cloud model clearly works the best, and the other Whisper models that you can run, small, medium, and large, don't run on the Jetson due to memory or latency constraints very well, so we had to discard those, although they work better. So we quickly ended up with a choice of two between Tiny and Base here. And the next question was really around modality, and there's really two ways to run these. The typical way, if you have an audio file and you want to transcribe it, is you do it in batch mode. You just submit the audio file, you transcribe it, which works reasonably well. The other is to run it in real time, right, where you're all the time transcribing. The trade-offs between these, of course, are that the word error rate for real time is worse. You don't have the future audio to look at when you're like in an offline mode. You do. So the word error rate is not usually as good. The latency is better because you're predicting all the time. You don't have to wait for the audio to be done in a real world situation. But on the other hand, the real time is using system resources all the time. So if you're trying to do multiple conversations or things like this, you have that trade-off. So there's these trade-offs in this case. And so we ran in the different modalities. The full batch gave you some sense. We didn't bother with the streaming for the cloud, but essentially you can see that you get slightly higher word error rates. Not that much worse, surprisingly, for this type of test set, which was really encouraging. And then we looked just for completeness at the time. So when you look at the full batch mode, clearly you have to wait for the audio to be done, and then you have to process all of it. It can take between 4 and 5 seconds. If you're running it all the time, it's much faster. The time of the last audio to the end, take 1.8 seconds. So it was not a very difficult decision in this case that the word error rate is substantially better, is substantially similar, and the latency is much better. For this application, we thought we wanted to produce more close to real time, so we went with this sort of streaming mode with Whisper Base. And this framework works similarly for other if we had more models, but just to give an illustration of it. Okay, so we spent more time around the LLMs and evaluating which language models we'd use. And here we looked at several of the large cloud models, so GPT-4, 4o mini, we looked at DeepSeek, we looked at Llama's 70 billion model, and then we looked at several models on the Jetson. So medium-sized models like Google's Gemma, Llama 3, Gemma, Mistral, between 9 and 7 billion parameters. And then the smaller models, Alibaba's Qwen, which has 3 billion, Llama, Hugging Faces, small LM, and then Llama 3, 1 billion. So a whole range from 1 billion all the way up to GPT-4o, and we'd evaluate some of these different models. And so given the task that we had, these conversations that had been transcribed, putting it through these LLMs, and then summarizing, this is essentially the output of these results. So they're not very surprising. They're almost in order by size, like we just showed, pretty much. So this is looking at with Whisper 1. So we did essentially the highest quality transcript first, just to see how well the LLM performs. And this is, again, F1 score. So F1 is essentially, the balance between precision and recall of what is being produced from the summary to the ground truth. So as you'd expect, the large cloud models perform quite well, the medium models, and all the way down. I think what's interesting and notable, though, is that the smaller cloud models and the larger edge models perform reasonably close to each other. So this is GPT-4o mini, and this is the Gemma 9b, and they're not dramatically far off. So even though it's almost 10x in parameters, but you're getting reasonable results at that point. I think it was also notable to see that DeepSeek performs quite well compared to these. Okay, so how do these behave over conversation length? So we started saying, this is one task. We had a variety of conversations. If we had a smaller set of, if the conversations were shorter or longer, would we choose anything differently? How does this behave in this regard? And what you see, again, I think nothing super surprising here, but is that the larger models, they reason better over the longer conversations than you can expect with the small models. You don't get a lot of gain. You're getting some level of these ones that are working okay, but you're missing out on a lot, and the larger models continue to do well. You can see the long model producing like 0.76 at GPT-4o level. I mean, producing much better than even these other models at even the short level for much of these. Okay. The other analysis we did was looking at how robust the model is to speech recognition errors. So essentially, can the model reason over speech recognition given the other context, right? So the Whisper 1 is sort of the best kind of cloud model, and these smaller models don't do so well. And you can see that in general, for sure, that that over the course of as you improve the models, you do better, which makes sense. And you can see as well that the medium models outperform the smaller models by a large margin. And that, again, speaks to the ability to reason over those kind of speech recognition type errors as well. This is a look at the accuracy versus conversation duration again, right? So these are all Jetson models. So this is just the Jetson, and this is looking with Whisper base. So this is actually real world sort of situation. We're running on the Jetson with the Whisper base model and with these Jetson LLM models, and you get again some sense how well these work. The medium-sized models, the 7B, 9Bs, they maintain the conversation ability over the longer conversations much better than clearly the shorter ones. Almost a 3x type behavior at the end, looking at F1 score, so take it directionally. Okay, so that is about the accuracy. So how do these perform from a latency perspective? So, because essentially, if we're looking at real time, clearly you'd expect some differences in this. And sure enough, it's the opposite, right? The small models are faster than the big models, as you'd expect. So the Hugging Face, which is advertised as a very fast model, is indeed fast. Average of 4 seconds over all the conversations, 2 seconds for the small ones, 5 seconds for the long one, and they go up. But you can see that the larger models take quite a bit of time. For the short conversations, maybe 6 seconds isn't too bad. For the long conversations, it's quite long, and on average. There was an interesting outlier here was the Llama 1B models. They're very fast from a tokens per second perspective. but they produce a bunch of garbage tokens, and so that they end up taking longer that way. So it's a fast but not very helpful model in that way. So but this gives you at least a sense realistically of what you're going to get from this, and just as a benchmark, you can see how fast the cloud models are from an inference perspective. You know, they're quite fast. So these LLMs take a lot of horsepower to run, is the bottom line. Okay, so how to pick a model for something like this? I mean, essentially, you know, there's no easy single answer here, right? There is the highest accuracy was Google's Gemma 9B. It's the biggest model and worked the best. The fastest is one of the smallest models, right? The small LM. And then in between, I think you have these two, which are reasonable choices probably, right? So if you are looking for slightly better accuracy and maybe just okay latency, the Llama 8 billion worked reasonably well for this use case. A little bit faster, and okay F1 is the Llama 3B, right? Quens is not bad either, and you can see the variations in this. So if anything, this is more to give a framework about how to think about this type of problem, and that it's not, you know, it's not a one-shot sort of figuring out these things. So let me show the demo and the results of this work. We're going to hope that this works, but let's see.
Hi, do you accept FSA card here?
If the audio is working.
Yeah, we do.
Can you hear the audio?
Use them for eligible over-the-counter products and prescriptions.
Very soft. Let's try it again. I'm going to put this here.
Hi, do you accept FSA cards here?
Yeah, we do. You can use them for eligible over-the-counter products and prescriptions.
And what about something like a first aid kit? Would that count?
Yeah, first aid kits are typically covered. If you are unsure, the receipt will label eligible items.
Oh, that's good to know. Do I just swipe the card at checkout?
Yeah, just like a regular debit card.
Okay. Great. So let me see if I can pause it there. Yeah, okay. So there were a number of transcription errors you may have seen there, and I apologize, this is a bit small, but basically, you know, was able to, this is an example of a case that worked for almost all the models. So the smallest models, like in this case, I think this is demoing Quen, worked quite well with this kind of use case. You heard it wasn't too long, but there were a number of speech recognition errors, and it was able to reason over all of those activities and produce a reasonable result, the outputs of which are here. So in simple conversations like this, we found generally, as you saw, that the models did reasonably well, maybe some mistakes, but decently well. However, and I won't show another video, but for many cases, the medium models were able to do much better than the small models. So here's a conversation, and I put the exact transcript that came out, you know, and it said, so like a suppressant with a very complicated drug can help for a dry cough. If it's productive, look for one. And instead of suppressant, it got super sand, and you know, that was a transcription error by the model, and it got passed on. Quen picked that up, whereas Gemma thought of that as cough medication. So when this conversation was classified, Gemma and GPT-4o, of course, were able to get these two topics out of the conversation, this clinical consultation, the service inquiry. Quen was able to get this service inquiry, but made some mistakes. Essentially, it gave like a bias towards the medical vocabulary, right, in this case, and didn't understand the full context. It wasn't robust to the ASR error and so forth. And it also made a third topic here. There is a topic about pills here, and it thought of that as a new product inquiry rather than being an extension of another thing. And so this is the instruction following of the prompt that says keep these consolidated together. It wasn't able to reason over that. So again, you can see the kind of problems that you see for these kind of models. And then in some cases, even you know, even the Gemma model didn't work well. So here's another case. You can see a speech recognition error. It says I'm trying to understand why my this is MS, it's an EMS, right? Medication suddenly cost more. So again, GPT-4o did a great job, was able to get this payment information insurance. Gemma failed to connect the fact that there was a discussion about price to the payment. It just thought it was about the drugs. It didn't really recognize this being about payments. Again, medical vocabulary bias, and it failed to understand the full context. And again, it also struggled with the longer conversation to follow instructions and separate it into a second topic. So the point in illustrating this is just to give some intuition around the type of challenges you see and the use cases that you'd have for having these kind of different size models and different type of behaviors. Okay, so I will wrap up this part with just basically the learnings and recommendations from something like this. So I think the challenges, there are a number, right? So still, to do this well at the edge is challenging, right? Running high quality speech recognition with low latency is hard at the edge for the reasons that we discussed. The complex language is hard, maybe even harder than the speech recognition. These models are very hungry. They take a lot of power to run. And it's very hard to get near real-time performance at the trade-offs, depending on what you're looking at. And I didn't really do too much on this, but throughput is also challenging because they consume tremendous amount of system resources. If you wanted to run an edge device and have several mics running or things like this, it becomes even harder because really tapping out the resources for just the one task that we're doing. But there are a number of areas where even with what we had works okay, and you can make even better. So first is, if you're working in the real world, you definitely want to give yourself the best chance to succeed, so better audio quality, right? Better quality audio, better mics, and then using array mics and things of this nature to improve speech recognition. Other is keyword boosting, custom vocabulary, and fine-tuning. So you can fine-tune a speech recognition model, something like a conformer CTC or other models, with your exact domain, exact type of audio, and really drive down the behavior, the word error rate. We could have explored other models for sure. We explored a very few cents. The other is, different type of modalities. We spoke about the real-time and the full batch, but you could do some hybrid where you do some small batch type of processing that may be not as fast, but also gives better recognition rates. And the other is to balance when you use real-time versus offline. So maybe having a very small task for looking for urgent matters that are real-time, and then maybe doing offline summarization for things that are less urgent. So maybe having specific tasks and running the processes differently depending on what's needed real-time, making the task easier, and then running something offline. For language understanding, I think there's a lot of possibility, a lot of headroom here. So I think the work that we did was general. We could have done the prompt engineering for a specific model. Pick one model and then just completely optimize for that model and make sure that it works well for that, as opposed to a general prompt and then evaluating the models. The other thing is to fine-tune the model for a specific data set. So running a training loop around, say, hey, we've got this training set of data, this set of conversations, these are the kind of summaries that we want. This can be done with actual fine-tuning, or it can be done with like dynamic prompting, where we say, here are some examples of what we want to have happen in this kind of edge cases. So essentially teaching the model to behave better for the cases that we know. So more effort in the model behavior, right? Similarly, tuning the model to be more robust to speech recognition errors, rather than just providing clean text in, providing messy text in so that it can get better and understand the domain and get smarter about those. And again, breaking the task down differently. Are there some cases where we just want to reason over very small things that we want to look for, and maybe for more complicated tasks like we had, run those in an offline or in a longer setting. And then in terms of performance, they're bigger, better hardware, right? So I think NVIDIA announced Digits, which is I think it's a slightly expensive device. I think it's $3,000 that's supposed to be coming out as an edge device, but it's got 25 times the computing power of something like the Jetson, and it's expected to be able to run like the 70 billion parameter models in faster fashion. So I think that's clearly, we can ride the Moore's Law curve here. Can explore other models as well. So we primarily used Olama, which is a very easy way to access all the models, but you can use specialized models, and you can also use other methods of those models. So like Tensor, RT, LLM, and there's other like customized models to the GPU and that are trained for that. We could have used things like that, may get 20-30% extra performance in those kind of situations. And last, I'll just leave you with sort of key takeaways. I mean, it is possible to build these real-time voice AI understanding at the edge. You won't likely get the same magical LLM behavior out of the box that we've become used to with ChatGPT and Claude. There's much more sort of work to be done to get this, and maybe appropriate to the task, at least today, where we sit with the hardware today and the models that we sit today. The good news is there's a number of levers to pull. There's a rich environment on the use case, the audio, the task that you can tailor to get the performance. And I think the other, of course, is models and hardware are getting better and faster. So today this is a complex task. Perhaps it will continue to get better over time. But I think there's a lot of promise and expectation for the use of edge for these kind of scenarios. And that's what I'll leave you with. Thank you. I'll happily take any questions. I think we do have a bit of time, right? Very little bit of time, or a few minutes if there's any questions?
15 minutes.
15, perfect. Great, we'll take it.
Hi, thanks for your insight. This is actually wonderful. We're doing similar projects, so I actually have a few questions. So you mentioned that you have been involved with drive-through, I guess, order
Yeah,
taking AIs.
automating the drive-through, voice
Yeah.
assistants at the drive-through,
Yeah,
right?
so two questions. The first one, I was reading some reports, I think it was McDonald's that had a project, maybe it was working with IBM Watson, but was a total failure. So I don't know if you knew any insight on that, you can comment on that,
Yeah.
question one. And
Yeah,
then-
it's a really hard problem. So I mean, McDonald's bought a technology and then spun that technology back out, and that technology now has, it's a little outdated. But the problems there are numerous. Both the speech, it's a wild environment, lots of noise, so speech recognition issues, the language issues, matching to the menu dependencies, and then all sorts of things like this. So it's a complex problem. The state of the art is working quite well, but it's still not perfect technology for that. The edge cases are huge. So I think that is the challenge. So I think McDonald's had started with one round of technology, and I think that field just keeps moving. So they're almost like 2 generations before where the state of the art is now. So I think it became hard to probably keep that up, is my conjecture.
Great. And the second question is with respect to another technology that just got released, I think earlier this week. It's called Sesame AI, and
Right.
and it's a very sort of like human-like voice.
Right.
And you can have a conversation, and the latency is almost zero, and it
Yeah.
feels like having a conversation with another human.
Yeah,
I don't
so
know if you know anything about
that's
that
great. Yeah,
technology.
so I think this is a super exciting time in voice AI in general. The typical model of speech recognition to natural language understanding and text-to-speech is being brought together in what was originally called spoken language models. So they're training right from audio, so you can pick out the intonation, you can pick out many things and have more natural language behavior. So right to the language model, going from audio and predicting those vectors and not having a discrete modal in between. So I think that is a very promising trend. And if you use even your real-time AI on ChatGPT, if you use that voice, has those kind of behaviors. So I think that is a very active area of research that is super promising, exciting. Not yet working well at the edge, but definitely I think it's promising for the future of more natural agents. Yeah, great question.
So you mentioned training the models with your specific vocabulary. Can you point to maybe software or techniques that you could use to do that for someone who's not really familiar with the field but is interested in it?
Yeah, for the language models, there's a couple different ways. I think the most straightforward way to start is just with prompt engineering like this, right? Is adding examples into the prompt. So you can think of this as like static examples to say, hey, this case didn't work well, think about this case, and you can add more and more and make a more and more elaborate prompt. So that's the most basic way to train the model, quote unquote. Second way is then to give dynamic examples. So based on what I'm seeing in the conversation that I've seen or something like this, can I go ahead and maybe fetch a few examples that are relevant? So you can think of if I have thousands of examples, maybe I can pull a few examples at that time and prompt the model dynamically with a handful of models. So you've heard of RAG and all of these things. You can embed the conversation, find a similar conversation or set of conversations, yank a few of those, and then give the model that. So that's like a dynamic prompting. So again, maybe it's a dynamic training. And the third is actually where you have a train test and you will fine tune, and that will require a little bit of the data science pipeline where you'd provide that kind of input data and you'd train and try to change the final layer of that model, the fine-tuned model. Many of the cloud models have it very easy to do. At the edge, you need to run it clearly in a place where you produce those weights. So that's maybe the most technical. But the other two are, I think, quite successful and work quite well. I'd recommend around. If that helps.
Okay. And on that, thank you, by the way. And on that topic of fine-tuning, did you do anything with fine-tuning the models themselves? Maybe doing this tuning of the model with like a derived model in Olama, for example, or some other sort of fine tuning?
So did we, in this case, did we, or? In this case, we didn't, but certainly, yeah, for other projects, we have had to do that. I think at the edge, I think it makes a lot of sense because you have a limited size parameter model that you can work with, and so fine tuning, if you've got a case that you're gonna run for a long time, I think it does make a lot of sense. In the cloud cases, the models are improving so fast, we haven't seen as many advantages these days in fine tuning in the cloud. You can do well with these other architectures and then just ride the advantages of the models that are due. So I think, yeah, we have done it in other cases. In this case, I hadn't done it, but yes, for sure you can. Yeah. Other questions?
Can Whisper distinguish between different speakers?
Diarization. So there are some modules that have some like diarization like this that'll add on to something like this. Whisper by default does not have that, I believe. So yeah, so I think you need to, and then I think there are some other models like Conformer CTC at the edge that you can add that diarization to where it'll distinguish and try to tell you who's speaking and not.
I had a question regarding on voice input. As you were saying that there's the crux of the question that's being, the prompt that's being asked, and then there's also the emotional aspect of things of, you know, the cadence, the anger, happiness, whatever. How is that data then sort of multi-threaded and then divided amongst where it needs to go? Where or when does that occur?
Oh, great question. So the question was about how does the emotion and other aspects of the audio make its way into the model for something like this. So to be crystal clear, in cases like this, in most cases, speech recognition is not taking account for any of that. It's purely taking the audio, transcribing it into text, and not accounting for those typically. I think the question that came up earlier was about, I'd say, some of this newer generation of models where they are embedded together. So they take audio as an input, and internally, the speech recognition takes place along with the language model. They take place together in a spoken language type method. So this system didn't use anything like that, and typically most systems we use today don't use that. I'd say it's relatively new that these later models are accounting for that and that are behaving much better for this. So, but the way they happen is internal to a model. You typically, we don't have ways easily right now where we separate those out, but the models are jointly trained. So you have audio input and then the output is trained, and there's maybe a layer in between in the model that'll account for some of these sort of vectors, if you want to think of it about emotion and likes, and then those are trained further on. So at least today, I don't know of any that separate those out and then use those in any intelligent way.
And I was also thinking in terms of that the more that evolves, it may then be able to sort of jump over that sort of humor aspect of things, which has such difficulty of understanding sarcasm and things of that nature, and that's sort of the paradigm where they're having such a difficult time discerning between when somebody says something and then they say it with an inflection, it means something completely different.
100%. Yeah, I think this is a super promising area, and I think the idea of separating out speech into text and maybe trying to get those other pieces and then put it into a model is too fragile. And so this much smarter way, and the way that at least currently is being innovated around, is where it's training all of those together, right? So it's pulling those out, keeping that vector internally, all of that data, and then trying to reason over those pieces with the language. So I agree with you. I think it's a very promising aspect. I think it might be a while before we see them at these edge models because they're much bigger and they have much more data around it, but I think there's a lot of progress in this. So I have even seen some, I haven't explored them myself, where some models claim to do that at smaller open source, but even I haven't tried them yet, so it's a great question.
Any more questions? If not, thank you, Zubair.
Great, thank you. Look forward to connecting and spending time with you. Appreciate the time.